All right, we are switching gears a little bit from exponentials and logs. Those aren't going away. We're just switching gears a little bit for now. And starting our trig units, that is really like a couple of units. That's going to be the majority of what we do for the rest of the year. The Greek alphabet, chose to talk about it now because we're going to start using it. You should be familiar with a lot of these Greek letters that you see in front of you and use them in your math, probably more so at this point in your science classes than a lot of your math classes. But I would say in school, probably pi is the first one that you're really introduced to. You may have already been familiar with the alpha and omega, before you actually learned pi. But a lot of those other ones should have come up, in maybe a few of them in geometry, and then in chemistry for sure, and a lot of them in physics. And the Greek alphabet is used as variables and as constants. So make sure you know the difference. Variables vary, hence the name variable. Okay, constants remain the same, hence the name constant. Okay, pi is a constant. It always represents the same number. We just use it so that we don't have to write out an infinite number of decimal places every time we ever write it out. So you can read this. I'm not going to read this to you, but it's a little bit about the Greek alphabet. You can read it. There are some different pronunciations for some of these, and sometimes it just depends on whether it's like the old school way to say it or what country you're in. But for the most part, most of them are said this way. I have the little pronunciations there for you. But gamma rays, I don't know if you've talked about those in science yet. You've probably at least heard of that. Delta you used in geometry for sure, in chemistry for sure, and probably so already in physics. What does delta mean? The change, okay? And it will always, no matter what language, what country you're in, these are universal. So they're symbols that are actually used in these, in these forms of math or science, whatever. Theta, that's our big boy and girl way to use unknown angles. So for an unknown angle measure, instead of x, theta is the kind of the go-to one. Alpha, beta, and gamma can also be used, but theta is the big one there that we got to make sure we know. And it's the lowercase theta. Then there's your pi. Sigma is summation symbol. I'm not sure mathematically if that's something that you've seen before or not. We definitely use it in here. Used to come up in Algebra 2, but I'm not so sure that y'all do that in Algebra 2 anymore. Then tau. Anybody know what tau is? The constant? Anybody know what constant it is? Okay. So Earth people, there are tau people that say that pi is wrong and tau is better and whatever. Although unlike the flat Earth people, the tau actually does exist. The tau is 2 times pi. Okay. Shh, listen. Pi is, your 3.14159, blah, blah, blah. Tau is 6.28, blah, blah, blah. It's 2 pi is what it is. And so there are times where tau makes more sense than pi does for whatever you're using. We'll talk about that a little bit today. But that's what that is, just so you know. And then phi, anybody know what, and this is probably what, if you know what it is, probably the way you would have seen it. Anybody know what constant that goes with or what it relates to? All right, have you heard of the golden ratio? Okay, so the 1.6 number that goes with the golden ratio, phi is the symbol that's usually used to represent that constant when you're doing that. If you are in any advanced art classes, or maybe even, I don't know what they do in Art 1, I have no clue about what goes on in art classes because I don't belong in there. But I don't know if you talk about it in Art 1 or not. But when you're trying to draw, what I've been told, because I would never even try, when you're actually trying to draw like a face, like a human face, not a stick figure face, I can do those. Those are really difficult to do, to get the spacing of the eyes right and the nose, and otherwise they just look all funky. But the golden ratio, thank you, is something that is used to help space those things out. You're in like an advanced sketching. Do y'all talk about the golden ratio? No? Okay. And maybe not, again, I don't know when exactly it would happen because I've never taught art. I would be the worst art teacher in the world. But anyway, so if you look at, well, here's the golden ratio. It's like the perfect rectangle. It's not too long, like a long and skinny rectangle is considered like the perfect rectangle. And that spiral there is your golden ratio spiral. Do y'all know what a nautilus shell is? Those really pretty seashells. A lot of times you get the cross section so you can see the inside. It has like that spiral shape. It's the golden ratio. If you are trying to draw like a human face or something, the golden ratio helps you get the spacing. If you were to look at someone and think, that they have a really beautiful face, most likely their proportions on their facial features are very close to the golden ratio, because we all have some sort of ratios, but here's where that kind of comes into play to get everything spaced right. And then on a profile, kind of how the golden ratio plays into the different things. So that's what phi is, just so you know. We're not using it right now, but just kind of a little FYI. I'm going to, now, there are a few reasons why you kind of need to know the Greek alphabet. First of all, a lot of these symbols are going to be used. It's important that you know what they are and what they mean, and maybe like how they relate actually to your physics or whatever that you're doing. The good news is that they're pretty consistent. Delta is always going to mean change. It doesn't matter if you're in chemistry and geometry and calculus and physics. It doesn't matter. It still means the change in something. But so learning it's good. I had a professor in college, well, most professors in college when you're a math major make you learn it, but made me learn it. But if you're going to go into a lot of sciences, you need to know what they are, how to say them, how to write them. Or when you go to college, if you're going to rush for a sorority or a fraternity, then they might make you learn it as part of that process. You can already know it now. I'm going to show you a quick little video of the alphabet.
Alpha, beta, gamma, rays, delta, epsilon, hey, 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 zeta, eta, theta, iota, then there's kappa and lambda, mu and u and xi, xi, omicron, and then there's pi, o, rho and sigma and tau 2, upsilon, it starts with U. Phi and chi and psi are fun. Omega, and then you're done. Learn all that and then you're set. That's the whole Greek alphabet.
So it's to the ABC song that you already know, which is also Twinkle, Twinkle, Little Star, in case you never knew that. But that's and some of those pronunciations, even in this video, are different than what you have on that paper, but they're pretty much, the same there. All right, so let's talk about the angles that we're going to get started on, because what we're working our way into is the unit circle. And there are two things that are huge snags for people when they get to calculus. Okay, number one is algebra skills. Having sharp, good, confident algebra skills can make it a torturous time for you. The second one is the unit circle. Not just having it memorized, but truly understanding it and how to think your way around it so you can get through the thought process and stuff quickly. That is something that I'm going to walk you through and help you learn. That's way better than you just memorizing it, because you can memorize it for a test and forget it. But if you don't know it, you are going to struggle in calculus. I'm telling you that right now. So if you're doing what I'm telling you to do as we go through this and you're truly trying to learn it, you will learn it. I will help you learn it. And then you will know it so that you can, get through these. What we're doing today, if you were in a pre-AP geometry class of any kind, then about 90% of this should be a review. If you were in an on-level geometry class, then about 50% of it's probably review for you. But all of it is important. So when things are a review, make sure that you are paying attention to the details, to the terminology. You have to know what these things mean, how to find them, how to notate them correctly, how to draw them, all that kind of stuff, so that moving forward, when we build on this, all this stuff just becomes easier and easier. So you should already know that we take angles and we can put them on the coordinate plane. That's something that comes up in geometry to get to the next part there. So it says an angle in the coordinate plane is in standard, that should say position. I don't know how I messed that up. Standard position. When the vertex is on the origin, so there's my vertex right there, and one ray is on the positive x-axis. So my angle starts here. Okay, and then it opens up, and this is the other side of my angle. Okay. All right, so the ray that's on the x-axis is called the initial side. That's where it starts. The other ray is called the terminal side because that's where it ends. So then when we open up, because we know that when it's closed, this is 0. So when we open up this direction, that's your theta there, just meaning like x. Your counterclockwise rotations result in positive angle measures, which means that your clockwise rotations result in what? Negative. And so when you first learn your quadrant numbering, it probably seems weird to you, like in pre-algebra or whenever you do it. Like, why would anybody choose to start with 1 over here? But that's because it's where our angles start. This is 0, and it opens up this way. So this is quadrant 1. This is quadrant 2, 3, and 4. You should never get that wrong. That should be an issue for you. I have no mercy where that is concerned, because that is old basic stuff. And if you can't get through that, I can't help you with anything else. And they are Roman numerals, okay? That's how you write them, Roman numerals. All right, so let's talk about degrees. Degrees is the only way you knew to measure angles up until you got to geometry, most likely. And so the most common unit of measure is the degree. Okay. So from here's 0, I rotate all the way around, that's 360 degrees, right? Which means a degree is equivalent to 1/360th of a full rotation. So we should be able to sketch these in standard form with the given measure. Most of the angles that we deal with will be in standard form. Not every angle has to be, but that's where most of our angles are going to come from. So we start with the initial side on the positive x-axis. Since this is a positive 135, we're going to rotate counterclockwise. From here to here is 90. And so if I subtract 90 from that, I got 45 left over. So I got to go 45 more degrees. Now, I'm not going to make you get out a protractor for this and make it perfect, but you should be able to estimate pretty darn close. Okay, don't just slop a little ray over there and think I'm going to take it. So if this is 90 degrees and I need to go 45 more, it's about halfway. It looks like that. Now, then this next part is important. It's what gets messed up a lot the first time it's taught, so make sure that you are doing this correctly. You have to draw in a curvy arrow that shows the direction of movement and shows your angle, but you got to make sure you place it right. You can't just slap a little curve on here and call it done. It starts on the initial side, and you're touching the initial side, not here at 0, but on the side somewhere, and then it shows you that you're rotating this way. The little arrow touches the other side, just like that. So you can see exactly what happened to open that angle. This is 135 degrees. Everybody good? Okay, so then 495. Is that more than one rotation? Yes, it is, because I start here, go around to 360, and I got to keep going. So I'm going to subtract 360 from this. That leaves me with 135. Well, that's what we just drew. So I know that my initial side starts here. My terminal side is halfway between those two like that. But it's my green arrow that I'm going to draw in here that makes these different. Because I start here, not at 0, but I start on the angle somewhere. I rotate around 360 degrees, and I keep going, and it looks like that. Bless you. Although they end up in the same spot, one has another rotation in it, so those clearly, when you look at them, are two different angles. Does that make sense to you? Okay. So then I've got this negative 140. I'm going to start here. Negative 140, what quadrant will I end up in? Third, right? So if I'm starting here and it's negative, I'm going to go this way. This is 90, and then how much farther do I go? 50, which is a little bit more than halfway. Probably hard to really distinguish on a picture like that, and that's fine. But there's that, and then this is my negative 140 degrees. Okay. Any questions about any of that? We all good? Simple enough? Yes, ma'am.
So we labeled those two. Do we have to label them?
Oh, yeah, I just missed it. What was it? 495. Thank you.
It's been in your last screen.
It isn't touching. Oh, close enough to touch it. Yeah. Thank you. And really, it doesn't technically have to like really be touching, but I can see jump like this. Just well, I don't even know that I can draw it in. But it would be like just an arrow that like went like that or something, and it doesn't even touch the angle. And I have a feeling the people that do that just have no clue why they're really drawing it anyway. But yeah. But thank you. Yes, please correct me when I'm not right. So now let's talk about radians. This is the whole reason that all this comes up in geometry, is because that's when you learn about radians, no matter what level of geometry you're in. So up until then, degrees is the only way you know how to measure angles. But we have radians, it's a unit of angle measure based on arc length. That's why it's discussed in geometry. So 1 radian is defined as the measure of the angle formed when the radius is equivalent to the length of the intercepted arc. So regardless of what the length of the radius is, whatever this is, that's the radius, so that's also this. That length, as far as arc length is concerned, would be 1 radian. Okay? That angle would be 1 radian long. That's clearly not a triangle, it's a sector of a circle. But if you think of it kind of as an equilateral triangle, all 3 of these little pieces would be congruent as far as length is concerned. So this is why we refer to the unit circle a lot. It doesn't matter what the radius is. If this is 15, this would be 15, this would be 15, all inches or whatever. But the unit circle kind of simplifies it all down. The circumference of the circle, the length all the way around, is 2 pi r. So if it's a unit circle, my radius is 1, what's the circumference? 2 pi, right? And if this, so it's the ratio of that to 1, so you're just done with that. So 2 pi is all the way around. 360 is all the way around in degrees. 2 pi is all the way around in radians, 1 full rotation. So 360 degrees is 2 pi radians or tau radians. Okay, that's one reason why tau is one of the many reasons why tau might be more helpful. Instead of tau, it's also easier just to use the reduced form of it. Yes, 360 degrees is 2 pi, but 180 would be what? Pi radians. So when we go to convert, it would help if I actually spelled it right, radians. So when we go to convert, if you know that there's 180 degrees for pi radians, that's like saying there's 1 foot for every 12 inches, and you just use that to convert. It's very difficult to convert wrong. It's either 180 over pi or pi over 180. Well, if I want radians and I'm in degrees, then I need pi in my number. So pi is the numerator, so I can multiply it in there. If I'm in degrees, if I want degrees and I'm in radians, I need to divide the pi out so it's in the denominator. Okay? I mean, if you end up with pi squared, you did it backwards. I mean, it's kind of hard to do it backwards. Degrees most of the time are whole numbers, so you'd want to put that over 1 and multiply. Radians a lot of times are already in fractions, but not always. So if it's not in a fraction, you would just put it over 1 and reduce before you multiply, and it's that easy. So we need to know how to convert quickly and accurately between degrees and radians. And then also, there are going to be some special ones that we're going to have to just know, and we'll talk about that once we get to the circle. So it says convert each angle measure to radians and state the quadrant. So 60 degrees, what quadrant would I be in? 1. Okay. So then I'm going to convert. I'm going to take 60 degrees, and since I need pi in that, I'm going to put pi over 180. Put that over 1. No need to multiply straight across at this point. Reduce before you do anything. The zeros cross out. 6 goes into 6 once. Goes into 18 3 times. And you're left with pi thirds. And for radians, we don't usually put the units on it. I know that seems weird. Like everything in the universe, we put units on, and you have to. And then radians, we just kind of don't. You could put RAD or radians, but it's acceptable to leave them off. All right, so let's look at 160. What quadrant would that be in? The second. So I do 160 times pi over 180. Put that over 1. Can cancel out the zeros. Half of 16 is 8. Half of 18 is 9. So I get 8 pi over 9. Now, as you go through this, the more you try and picture and relate things to the unit circle, the better off you're going to be when we actually get to doing everything else with the unit circle. Think of this. If I have this, as I go around, I'm going to do 90, this is 180, this is 270. One thing that you need to start doing, which will simplify things for you, okay, so this is still 0, or if I go all the way around, it's 2 pi, right? That 180 is pi. So what do you think 90 would be as far as radians is concerned? Pi over 2, right? So pi over 2. So you want to be able to think fractionally with whatever kind of fraction you have. We have halves here. So you want to think about it this way. This is 0. This is pi halves. So I go another 90. That's 2 pi halves, which is really just pi, right? You'd never write 2 pi halves, but being able to think that way is good because I got 0, pi halves, 2 pi halves. What would this be? 3 pi halves. This will be 4 pi halves, and that's where the 2 pi comes from. Does that make sense? So whatever the denominator is, think in those little sections and think in like kind of the unreduced form to get you to the next part. That will help you greatly. So with that said, look at that 8 pi over 9 we got. We already know it's in the second quadrant, but that was because it was degrees and we felt it. So I want you to think about if it was in radians, could you go ahead and reason through that even though you're not super comfortable with radians yet? If this is 0 and this is pi, that 8 pi over 9 is almost 9 pi over 9, right? And wouldn't 9 pi over 9 be just pi? It's a little bit less than pi, so that tells you it's in the second quadrant. Does that make sense? So try and relate that as much as you can. Don't just blow through the homework and get numbers for the sake of getting numbers. The more you can make sense of that now, when we really get a circle in front of us and start doing other things, it will all make a whole lot more sense, okay? But if you just blow through and get numbers or don't do it or whatever, you're just going to continue to struggle through all of it. So, like I said, I'm going to walk you through it, but you can't be resistant in the process. So, negative 330, what quadrant would that be in? Be in the first quadrant, right? Because it's negative, so you'd almost go all the way around. So I'm going to take negative 330, multiply it by pi over 180. Put that over 1, knock out the zeros. Can divide this by 3 and get 11, this by 3 and get 6. So I get negative 11 pi over 6. So even without knowing the degrees, isn't that almost 12 pi over 6? And 12 pi over 6 would be 2 pi, right? So you're almost at 2 pi. So take those fractions and really start trying to think about them. If you're afraid of fractions still and you can't, I mean, it's going to be hopeless for you at this point. You're going to have to get over it. I don't know what to tell you. But all right, so let's look at 7. So before we even convert, because again, I know that you're not super comfortable with radians right now. It'll take a little while, but eventually you're going to like radians way better than degrees because they actually make more sense. There's a whole lot more patterns in there which can help you get answers very quickly, where with degrees, the numbers just get big and weird. But so for this, we've got 5 pi over 18. Well, clearly we're not anywhere near pi, right? But if it was pi halves, what would that look like? What would that be? 9 pi over 18. So we're not even at 9 pi over 18, which means we have to be where? In the first quadrant. You see how that works? Even if you don't know exactly where it is, I don't expect you to look at this and be able to tell me the angle measure like that, or the degree measure, but you should hopefully be able to think through the quadrant right now, okay? That's quadrant 1. This is also not one of the ones you would just have to know, but you need to be able to convert. So I've got 5 pi over 18 times 180 over pi, because I need the pi to cancel out. And see, the radians were already in fractions, so it's kind of already set up better for me. The pi's cancel out. 18 goes into 18 once, goes into 180 10 times. So then I have 5 times 10, which is 50. And it's not okay to leave the degree symbol off. We good? All right. So negative 11 pi over 9. What quadrant do you think that would be in? Second, because if I'm here and it's negative, this would be pi, which would be 9 pi over 9, right? So I just have a little bit more to go, and I'd be in the second quadrant. Okay, good. So negative 11 pi over 9 times 180 over pi. So I'm going to cancel the pi's out. 9 goes into 9 once, goes into 180 20 times. So negative 11 times 20 is negative 220. So as you go through this, come up with a quadrant when it's in radians. When you find the degrees, then see if you agree with yourself. I mean, if you were wrong, fix it, but try and do it like not necessarily the easy way so you can start processing through those thoughts. All right, so 7 pi thirds. I would really appreciate it if y'all would stop talking. If you have a question, ask me. Otherwise, just stop talking. 7 pi over 3, what quadrant would that be in? Do you agree with that? Yes, because, so 3 pi thirds would be pi, right? And then 6 pi thirds would be 2 pi. And then so it's a little bit more than 2 pi, right? So I'd be up there in quadrant 1. So that means 7 pi thirds times 180 over pi. And then cancel the pi's out. 3 goes into 3 once, into 180 60 times. So that gives me 420. So since I already knew it was more than a full rotation, then I knew my answer should be more than 360. And so hopefully that should make sense in the end. Okay. Any questions at all? We're good so far? All right. Okay, so coterminal angles. Again, terminology is important here too. You got to know what it means to be a coterminal angle. So angles in standard position with the same terminal side are coterminal angles. That means there's different ways to get there. If we were to go out on the track and we were to run a bunch of laps, and then we have to, no, don't worry, we're not doing that. You'll never do that in here. Run a bunch of laps and we end up back at the start-finish line, right? We'll all end up in the same spot, but some of us will have run a whole lot more laps than I did, okay? Like you could all run different amounts of laps, but we all ended up in the same spot. Same kind of thing with the angles. They could have more rotations. That's what happened here. When we graphed these are coterminal angles because they end up in the same spot, but they're actually different measures. Does that make sense to you? Same terminal side, just a different way to get there. These went in the same direction. We could also go in the opposite direction. So one angle has an infinite amount of coterminal angles because you could keep going in either direction, however many rotations. So this says to determine whether two angles are coterminal. So if I had to find a coterminal angle in degrees, how do you think I would do that? What would I do? Okay, you could. Well, let's just say, I'm not asking you how to solve that necessarily, but I have an angle. I want to find a coterminal angle for it. What would I do with that number? I could subtract that from 360, but instead of subtracting that from 360, take the angle and then do what? Add 360 or subtract 360, right? Because wherever my angle is, if I go this way, I'm adding 360. If I go this way, I'm subtracting 360, right? Or any multiple thereof, 2 times 360, 3 times 360, because I can keep going. Does that make sense? So what I'm trying to determine whether or not they are coterminal angles, and this is negative 55, I can take that 305, subtract 360. That gives me negative 55. So are those two angles coterminal angles? Yes. Okay. So then 30 and negative 170. So if I take 30 and I subtract 360, I get negative 330. Now, just because the number you get doesn't initially match what you might be trying to see if it's coterminal or not, doesn't mean that the answer is no. It could be, but you may just need to subtract again or add again or whatever. But is there any multiple of 360 that I could add or subtract to that to get negative 170? No. So since I can't, that's what I get, so my answer is no. So then I'm adding or subtracting what? 2 pi. Okay, so I'm going to start by subtracting, I guess. I'm going to subtract 2 pi, but I don't really want 2 pi. Yes, I need a common denominator, but don't think of it that way. You're thinking in fourths. So instead of 2 pi, what would I write? 8 pi over 4, right? So I'm really taking pi fourths and subtracting 8 pi fourths, and that gives me negative 7 pi fourths. So are these coterminal angles? No.
So you just subtract
Well, when you're trying to compare them, it just depends on what the second one is. Maybe I'd need to add. Like if this was a positive number, I would need to add something, not subtract something. So I'm going to take 3 pi halves, and I'm going to, since this is negative, I'm going to subtract what? How do I write that? Because yes, it's 2 pi, but in disguise it is what? 4 pi halves. So when I do that, I end up with negative pi halves. Are these coterminal angles? Yes, because I do it again. These don't initially match, but if I subtract 4 pi halves again, I get negative 5 pi halves. So the answer then is yes, they are coterminal angles. Okay, everybody good with that? Any questions? All right. So then it says give two coterminal angles. And remember, there's an infinite amount of answers, but the simplest ones would be the best. But it does say one positive and one negative. So I take this 150, and I can add 360 to it. When I do that, what does it give me? 510. So that's one coterminal angle. And then I can take that 150 and subtract 360. Now, when I did that, if I still got a positive number, then I might have to subtract again. But I don't. I get a negative what? 210. Okay. Then I have 7 pi sixths. I'm going to start by adding 2 pi, but in disguise, that would be what? 12 pi over 6. So when I add those, I get 19 pi over 6. Then I take it and subtract that. So 7 pi over 6 minus 12 pi over 6. And that'll give me negative 5 pi over 6. Okay. So then negative 11 pi over 12. I want to add 2 pi, but in disguise, that would be what? 24 pi over 12. So when I add those, I get 13 pi over 12. So there's my positive one. Then negative 11 pi over 12 minus 24 pi over 12 equals negative 35 pi over 12. So you get one of each there. Okay. Any questions at all? Okay, so reference angles. Reference angles are hugely important because we're going to use the heck out of those, and truly understanding reference angles and being able to visualize them on the circle and how they work is going to help simplify a lot of stuff for you. So you got to make sure you know exactly how they are very simple, but making sure that you're doing them correctly and you understand the true definition of what they are. So your reference angles for an angle theta in standard form, the reference angle is, here's some very important words, positive acute angle formed by the terminal side and the x-axis. I don't care if you're closer to the y-axis. It goes with the x-axis. And it is always positive. It does not matter which direction you go to get there. It is a positive angle, always, and it's always acute. Okay? So here's my theta, right? So this is the actual angle. The acute angle that gets you to the x-axis is right here. This would be the reference angle. Okay? So let's graph this 150. To graph that, it's going to start here. It's going to rotate around. It's more than 90. How much more than 90? 60. Now this is 90 degrees, so 60 is like 2/3 of the way. End up about right there. So this is your 150 degrees. The reference angle is created by the terminal side and the x-axis right here. So this would be how many degrees? I guess I need that earlier. Confusing. 30 degrees, because it would take me 30 more degrees to get to 180. All right, so this is 30 degrees right here. Everybody okay with that? That makes sense? Okay, so 315, what quadrant would I be in? Fourth quadrant, right? So I'm starting here, I'm going all the way around, and how much more do I have to go to get to 360? 45, right? So that means it's halfway through here, like so. This is 315. So then this is my reference angle right here. And because I asked you, or myself when I'm graphing it, like how much more do I have to go so I know where to put it. When you ask yourself those questions, you come up with the reference angle. Well, it's 45 more degrees there to get to the x-axis. Okay, everybody okay with that? So negative 240, what quadrant would I be in? Second one, because I'm here, this is negative 180, right? And then I would have to go how much more? 60. So that's again like 2/3 as I'm going, so it's about right there. Here is your negative 240. And then this is my reference angle. So this angle right here is going to be how much? How many? 60. Because I go 180 and then 60 more, so this is 60 degrees right here. Okay, everybody okay with that?
Yes.
Any questions at all? All right. So then let's look at the one with radians. So 5 pi thirds. Can you tell me at least which quadrant we would be in? What is 6 pi thirds? 2 pi, right? So we're almost at 2 pi, so I'd be in the fourth quadrant. So let's think about this. This is 0. This is pi, which is 180. So pi thirds would be how many degrees? If this is 180 and it's pi, then pi thirds would be a third of that. What's a third of 180? 60. So pi thirds is 60, right? So this 5 pi thirds, I'm here, I go around, and 6 pi thirds is 60, but I don't make it all the way, so I've got it about right there. I know that you are not super comfortable or comfortable at all with radians right now. If on some of these you need to actually convert that to degrees to wrap your mind around the angle, that's okay. You don't have to, but if you need to for right now, that's fine, because it's part of that learning process. But then we have to make sure you're putting your answers in radians if that's what you're doing. So since this is 5 pi thirds, then I got to get all the way to here would be 6 pi thirds, so I've just got pi thirds left to go. So 13 pi sixths. Tell me about that. What quadrant would that be in? First, because 12 pi sixths is 2 pi, right? So I'm going to go all the way around and then a little bit more. I go pi sixths more. Well, if pi thirds is 60, what's pi sixths? 30. Okay, so it's about 30 degrees right here. So I'm here, and I go all the way around and then keep going. There's my 13 pi over 6. So this is my reference angle, terminal side and x-axis. So we just said that we went all the way around. That's 12 pi sixths. Then I go 13 pi sixths. That's pi sixths. I can't even say it right. Sixths more. All right, negative 5 pi fourths. What quadrant you think you were in? Because 4 pi fourths is how much? Pi, right? So negative pi is right here, and then 5 pi fourths would be another pi fourths. Well, if 90 is pi halves, what is pi fourths? 45. So I start here, and I'm here, and it goes like this. This is negative 5 pi fourths. So since negative 4 pi fourths is 180, and I just got to go one more, this right here is pi fourths. And it's positive because it's always positive and it is always acute. Okay. Any questions at this point? So do you understand how to think fractionally as you go around? Just make it into whatever that denominator is. All right, so these coterminal angles is new for everybody for sure. They're simple, but I probably haven't heard I just said coterminal. I'm sorry, quadrantal. If I ask you what quadrant it's if it's on an axis, it's not in a quadrant. Would you agree with that? So they're called quadrantal. There are 4 quadrantal angles. So if I said, what quadrant is it in, and you can't say 1, 2, 3, or 4, you say it's quadrantal, like you have to use this word, but I'm not going to write it over and over here. And then this right here, that's when we're at 0 or 2 pi or 360 or any multiple of that. If you land there and that's your terminal side, then it's quadrantal. Plus you have to tell me that it is on the positive x-axis, so you distinguish between all of the other quadrantal angles. If it's at 90 or pi halves or any multiple of that, okay, that's another quadrantal angle. And then you would tell me this one is on a positive y-axis. Your 180 or pi or any multiple of that is quadrantal and on the negative what? X-axis. And then 270, 3 pi halves or any multiple of that is quadrantal and on the negative y-axis. And no, you cannot abbreviate quadrantal. Somebody's already asked me that, because if you just put quad, what does that mean? Quadratic, quadrilateral, quadruplets? I don't know. So quadrantal. You need to write it out so you know what it is. Any questions? All right. So go ahead and glue or tape that in, whichever you'd rather do. And on your assignment where you convert, on the notes it said name the quadrant. I left that off of here. I'm not going to count it wrong if you don't do it, but I highly suggest that you do it and that you think through it. That's going to help you make sense of it on the coordinate plane so that everything else makes more sense moving forward. Okay.